We learn about calculus in high school, and we know it includes integration and differentiation. But what does it actually use for and how? The language of calculus appears everywhere in modern science and technology, whether we're modelling the rise and the fall of the stock market or determining exactly when a space rocket will arrive into Earth's orbit. It's the language invented for the specific purpose of describing the dynamic nature of our universe. To put it simply, calculus is the maths of motion and change. The word calculus originates from the Latin word meaning pebble. The Romans used pebbles to perform calculations on an abacus, and the word became associated generally with computation, just like the word calculator. The beauty of calculus is not just in the maths alone. It's in the way that calculus can form a connection, a relationship, and a language to describe the dynamic nature of our world. There are unlimited uses and benefits of calculus in any field. Calculus is the language of motion and change, and by using calculus, we have the ability to find the effects of changing conditions on a system like the weather, for example. In the atmosphere, we have changing temperature and changing pressure. So by using differential equations, meteorologists can indicate and predict the weather for our benefit. Calculus holds incredible power over the physical world by modelling and controlling systems. It's the language of medical experts, scientists, engineers, statisticians, physicists, and economists. If a quantity or a system is changing, we can use the mathematical modelling of calculus to analyse the system, find an optimal solution, and predict the future. Motion, electricity, heat and light, harmonics and acoustics, astronomy, radioactive decay, reaction rates, birth and death rates, costs and revenue, all of these can be modelled beautifully using calculus. In calculus, we have two different branches. The first branch is differential calculus, and this involves the concept of the derivative of a function. This branch of calculus studies the behaviour and rate at which a quantity like distance, for example, changes over time. When we use the process of differentiation, we are essentially analysing the changing rate of a quantity and making predictions about its behaviour. So by finding the derivative, we can find the exact instantaneous rate of change at any point we like. If a function has a constant rate of change, we get a straight line, and it's easy enough to just find the rate of change using rise over run. However, when a function changes its rate a multitude of times, by using differentiation we can find exactly what its instantaneous rate of change is at any and every point in time. The second branch of calculus is integral calculus. Integration is the reverse process of differentiation, sometimes called anti-differentiation. With integration, we can describe the area of a 2D region with a curved boundary, or the volume of a 3D object with a curved boundary. We integrate by breaking the region apart into thin, unlimited vertical rectangles of equal width until the width of the rectangles virtually becomes zero, which is called a limit. This limiting process allows us to calculate areas and volumes with exact precision. If we differentiate a function and then integrate it, it will always take us back to where we started. Both these branches, differentiation and integration, are connected together by something called the fundamental theorem of calculus. This theorem, created by Newton and Leibniz, states that differentiation and integration are inverse operations or opposites, just like yin and yang, black and white, or matter and antimatter. Take the square root for instance. The opposite of taking the square root is squaring a number, just like differentiation is the opposite or inverse of integration. Now that we know what calculus is, wouldn't it be interesting to see how it can be used in aerospace to describe a rocket launch? If an object is in motion like a rocket, we can use calculus to model it. The thrust of a rocket into space is based on the calculus of motion, which physicists term momentum. In rocket physics, we are applying Newton's second and third law to a rocket that has a variable mass. How is the mass variable? The rocket's mass is decreasing over time as the fuel propellant is being burned off. As the rocket propellant ignites, the rocket experiences a very large acceleration as the exhaust exits out the back of the rocket at a very high velocity. This backwards acceleration exerts a push force on the rocket in the opposite direction, causing the rocket to accelerate upwards. The force acting on the rocket, called the thrust, is the rate of change of momentum, which is the first derivative of momentum. Using calculus, momentum, or the amount of motion of the rocket, p equals mass times velocity, and so the rate of change of momentum, p' equals dmv dt, the thrust of the rocket. We can also write this as a physics equation, F equals ma, Newton's second law, and rewriting this from a calculus standpoint, F equals m times by the first derivative of momentum dv dt. To put it simply, the thrust of the rocket during a launch is the first derivative of momentum. Rocket propulsion also employs Newton's third law, conservation of momentum. This dictates that if material is ejected backwards, like the exhaust in a rocket launch, the forward momentum of the remaining rocket must increase because an isolated system can't change its net momentum. In other words, for every action, there is an equal and opposite reaction, Newton's third law. After launch, to achieve the desired final orbital velocity around the Earth, or to escape from Earth's gravity, the mass of the rocket must be as small as possible, and so the rocket sheds mass by using different rocket stages, separating its parts, such as the rocket boosters. Now that we've seen calculus applied in the physics world of aerospace, let's see the benefits of calculus in the world of economics. A lot of people dream about running their own business. Wouldn't it be great if you could work out exactly how to maximise your business profits and help build a thriving company? Well, calculus can be used to maximise profits and revenue for any business. In actual fact, calculus provides the language of microeconomics and the means by which economists can model and solve financial problems. Let's see how we can apply calculus to maximise your profits in your theoretical video game business PowPow. Revenue function is given by Rx. Marginal revenue, R-X, is the first derivative of revenue. This is the increase in revenue generated when producing one additional video game. Change in revenue divided by change in quantity of video games. So what this tells us is exactly how many units you should sell to maximise your revenue, so PowPow doesn't lose any money by producing too many units. This also takes into consideration the fixed costs of producing a big batch of video games. Let's say your business PowPow currently sells a new game, Legend of Horus, for $50. This makes the marginal revenue change in Y over change in X, so $50 over 1, which is $50. Now you want to increase sales by lowering the cost of the video game to $30. The marginal revenue gained by producing the second video game is change in revenue, so $50 minus $30, divided by the change in the quantity of video games, 1, which equals $20. But this is less than the price that you wanted to charge for an additional video game. As you can see, we have a financial problem here, and we need to model the revenue here using calculus to find the optimal quantity of games to maximise your revenue. Let's say we model the revenue for PowPow and produce the revenue function as Rx equals 100x minus a half x squared, where R is the revenue and x are the number of video games sold. If we graph the revenue function, we get a concave down parabola. Marginal revenue is the first derivative of revenue. Differentiating the function, we get R' of x equals 100 minus x. R' of x is the gradient function of Rx, so the change in rate of revenue, which is called marginal revenue. If we find the maximum revenue from the first derivative algebraically, we need to let the first derivative equal 0 to find the maximum x point or maximum number of video games first. Letting R' of x equals 0, we get 100 minus x equals 0, and solving this, x equals 100. Substituting x equals 100 back into the revenue equation to find the actual revenue for PowPow, your revenue is R of 100, which equals 100 times 100, minus a half times 100 squared, which equals $5,000. This means that the rate of production resulting in maximum revenue occurs when the number of video games sold is 100, resulting in a total revenue of $5,000. As you can see, we can easily maximise your business profits by using the first derivative of revenue, marginal revenue. It's also known that a company produces best results when production and sales continue on until marginal revenue equals marginal cost. So now that we've seen the benefits of calculus in aerospace and economics, let's now see its benefits in medicine. Let's say that you're a doctor, Dr. Cure, and you would like to observe the progression of a tumour in one of your patients, John. John has a small, early onset tumour, and you would like to see whether it's responding to a new innovative drug, a Rivadoci tumour, which has no side effects. As a doctor, you would like to model the growth of John's tumour using calculus to analyse the progression or reversion of his disease. The function you have created to model the progression of growth of John's tumour is an exponential function with respect to time. Vt equals v0 e to the power of at, where v is the volume of the tumour, v0 is the initial volume of the tumour, a is a constant and t is time. Differentiating this, the first derivative of the tumour volume will be the change in tumour volume over time, and in medicine this is called the specific growth rate, SGR, dV dt, or V'. The first derivative V' gives you important information about whether John's tumour is growing or shrinking, and the rate at which it's doing so. V' tells Dr. Cure the relative change in tumour volume per unit of time. Dr. Cure differentiates the function and produces V', so specific growth rate equals V0 times A times e to the power of AT, so V' equals V0 AE to the power of AT. If the tumour has a high SGR or V', Dr. Cure can interpret this as a rapidly growing tumour, and then he can make decisions about the form of therapy or change in therapy to cure the tumour and get John back to good health again. If the SGR is low, then Dr. Cure can assume that the new innovative drug, arivadoxi is working, the tumour is shrinking, and just continues John on the current regime. As we've seen, the beauty and benefits of calculus can be applied in any scenario of change or motion, whether it be aerospace, economics, medicine, and more. The benefits of calculus are endless, and if we have any problem in any dynamic situation that involves either change or motion, you can be sure that we can turn to calculus as a tool to model the problem and provide us with the answers.